Robotic aircraft, planes that can fly on their own without a pilot, have become the particular fascination of our group of experimenters. RC, or radio-controlled planes, have been around for decades, but until recently, UAVs, unmanned aerial vehicles that can fly autonomously with no input from the ground, belonged only to NASA and the military.
And autopilot is on. It's flying itself.
I invited a small band of UAV hobbyists I'd met through blogs and emails to join me at a Saturday morning fly-in near San Francisco.
Welcome to the Alameda Naval Air Station, retired Naval Air Station base. There's a couple things you should know about the surroundings. These fences here refer to areas that are either wildlife preserves, wetlands areas, Superfund sites that are polluted, or some of them do have unexploded ordnances. So basically, if the planes go over the fence, they're lost.
Got into stable orientation now. Here goes the autopilot. And there we go, we're under autopilot orientation control. As you can see, the helicopter is sort of trying to maintain its own orientation now. Orientation is all under the computer, so that's all software.
30 years ago here in the San Francisco Bay Area, the personal computer revolution was started by a bunch of amateurs, the Homebrew Computing Club, who recognized that the chips and boards necessary to make a computer were now pretty much within reach of amateurs, a couple $100, etc. The point is to make it yourself. The point is to do something for less than $1,000. And now, at this point, you're getting into programming, but it's something that no one's done before, and you're sort of exploring new territory. You're basically controlling robots in a three-dimensional fluid, where wind is unpredictable, where altitude is unpredictable, where the signals can end. And now you understand why NASA spends millions of dollars on UAVs.
In the spirit of do it simply, Jeffrey Johnson and Stuart Long are equipping their inexpensive UAVs with cell phone cameras to take aerial photos. Their plane couldn't be simpler to launch. Turn it on and throw it into the wind.
The phone has the camera on it, and the phone communicates with the GPS over a Bluetooth signal. So phone captures an image, assigns location via Bluetooth, and saves it to the device.
Their aerial images can then be displayed in Google Earth, the internet mapping program.
We're both geography guys. We both have degrees in geography, and we do GIS, Geographic Information Systems. So we're actually trying to turn the photographs that come from the UAVs into geodata.
That geodata places each image at a precise point on the map so they can monitor anything you'd like to see from the air.
All these images get referenced to the Earth, and from that we can extract useful information from that. So property lines, streets, runways, vegetation health, construction sites. We can watch the progress of those.
Only a few years ago, to get a set of aerial photos, you'd have to find a plane, pilot, and a photographer. Now you can look for a guy with a flying stick and a pocket camera. You could call Patrick Egan a minimalist among UAV enthusiasts. He works with a sliver of wood with wings and a camera strapped to it.
This here is a very rudimentary system. Obviously, it's a stick, 3/8 by 3/8 by 36 inches long. It has a lot of capabilities. You can get some really high quality photographs with this.
Hacking the latest consumer technology to use in robotic flying is part of the challenge.
We decided to get together and try to get the iPhone up in the air to do some aerial photography. And we ran into one unique problem with the iPhone, and that the iPhone is smart enough to know what a finger is.
So, how do you touch a touchscreen when it's a couple hundred feet in the air? Need a finger substitute.
My friend Ben discovered that if he took a French fry and he touched the French fry to the screen, he was able to get the program to trigger. So then we had to think about how we could do a French fry up in the airplane.
So how we overcame that was a servo with a Q-tip, obviously here, saline solution, and 3 volts were charged to this wet Q-tip head with the saline on there. And then it just came down and actuated the trigger button.
There we go. And we had an iPhone up in the air taking aerial photography.
Robotic helicopters are an even bigger challenge than a fixed-wing aircraft, since they're more unstable in the air.
So what we have here is, well, it's sort of an ongoing project to make a helicopter stay in the same place on its own. I started everything from the integrated circuits upwards. I had to build myself just to save money. So here we have the inertial measurement unit. This is sort of the heart of the autopilot. This tells the helicopter how it's tilted, where it's pointing.
By day, Adam is a computer programmer for a cable TV company. Feeding his UAV habit is costing him about $200 a month.
5 years ago, it was impossible. Really, only recently have these sensors become economical. I'm up to the $2,000 level because stuff breaks and new functionality is needed.
But what if you had some real money to spend on a UAV helicopter? It might look like this. We went to NASA's Ames Research Center at Moffett Field, California. It's the place where NASA tests a lot of its advanced unmanned flight systems. Chad Frost heads up some of the UAV work at NASA Ames. Our first stop was the NASA Army Autonomous Helicopter, originally built for crop dusting in Japan.
Yamaha has built several thousand of these in Japan just for that purpose, for going out and fertilizing and spraying insecticide on rice crops.
NASA and the Army have turned the little crop duster into an autonomous UAV that can take off, fly a complex mission like inspecting a hard-to-reach disaster site, then return home and land, all on its own.
That's another thing they're currently flying right now, using both the laser or stereo vision. You can look at the environment and completely autonomously the aircraft will come down and make the decision about not only where to land, but pick the safest place to land and do it completely without a human in the loop. They treat these things as farm implements.
Right.
They take them out in the back of a pickup truck, offloaded on the edge of the rice paddy, and go around and spray the fields.
So Japanese rice farmers are also radio-controlled helicopter pilots?
That's right.
NASA has added a few mods not needed by the rice farmers. A rotating laser scanner in the helicopter's nose can paint an accurate 3D picture of what's in front and below the aircraft. Inside the control trailer, the helicopter's cameras and sensors feed the monitors, and the ground-based software tracks every move.
This is a map display that tells you where it's going and what it's doing. This is actually the taxiway we're operating from. This up in the upper left corner is a virtual reality representation of where the aircraft thinks it is and where the aircraft thinks it's going.
The red ball represents its target.
Yeah. So this is where I'm going.
NASA's UAV fleet ranges from small helicopters to large modified Predators that can be used on long-duration missions, helping battle forest fires where it's too dangerous to send a manned airplane.
You can move the engine to the front.
NASA ecologist Matt Fladeland wants to use a UAV for climate studies.
We see UAVs as an area for providing measurements that we just can't get right now. One project that we're looking at, we're actually trying to measure fluxes of carbon out of systems like forests or out of the ocean. And so we need to fly very, very low in those cases, 30 feet above the surface.
The decision to use a UAV versus a manned aircraft often comes down to the flight's length and pilot safety.
In the case of UAVs, typically those are selected for missions that are either very dangerous or they're very long duration. They're so long that there's regulations on how long a pilot can fly.
At a lab next door, NASA engineer Corey Ippolito heads up a group trying to make UAVs more reliable.
We do experimenting on small-scale vehicles, very low cost, very cheap, very rapid prototype type testing and experiments.
These robotic all-terrain vehicles are able to communicate with UAVs circling overhead to provide radio relays and extra position information.
The robot cars help the robot airplane find out where it is.
That's correct. If something occurs on the aircraft, for instance, while it's landing, it needs ground sensors. You have all the sensors that might be needed in order to tell where they are, and more importantly, be able to tell where the aircraft is as it's landing.
How can people get a job here? Look at this place.
The appeal of this is that it's something that's never been done before. This is, in a sense, the uncharted territory of computing right now. It's taking computers into the air, giving them autonomy, making them standalone drones that can do whatever. It's a hint of doing what NASA and the military does, but it's within reach of amateurs.
30 years ago, amateur builders used the spare parts of the computer industry to change the world. If personal UAVs someday become as common as manned aircraft, who knows how we'll use them? For Wired Science, this is Chris Anderson.
Why can't people regenerate?